Welcome to today's RSECTION training. My name is Sonja von Bloh. I hold the training together with my colleague Paul Kieloch. Paul, perhaps you would like to introduce yourself.
Hello everyone, my name is Paul Kieloch. I'm working as a structural engineer at Dlubal software and there especially in the product engineering and in the customer support. And today I will answer your questions. If there are any questions, I will try to answer them as soon as possible.
First, I would like to show you how to use the training interface. It's possible via the button to show or hide the panel. The settings allow you to adjust your audio settings. There's also a chat function. You can use the window at the bottom to send us questions and comments. We try to answer these questions within the training. If there are too many questions that cannot be answered today, you will definitely receive an email afterwards. You don't have to give hand signals. You can just use the chat function. The training is recorded. This will be sent to you after the training. You also get all the models used. I would now like to give you a brief overview of the training series. In today's training, you will receive an introduction to the strengths of materials. This training builds on the first training, which explained how the internal forces are calculated. In today's training, you will learn how the cross-section values and stresses are calculated. In the upcoming training courses, you will then receive an introduction to finite element analysis and then an introduction to our design modules. This brings me to today's training program. I will first give you an introduction to the RSECTION program. Using several examples, I would like to show you the modeling options and design methods in the program. On the first example, a thin-walled eye profile is modeled with graphic functions. I will model this slowly so that you can enter this cross-section as well. In another example, I show how to insert cross-sections from the database and how you can add other parts to these cross-sections. Then I show the modeling of a massive cross-section based on an DXF template. Finally, I model a hybrid cross-section. First, I start a survey to find out whether strengths of materials has already been covered in your studies. I ask you to answer this now. Okay, most of you have already got info about strengths of materials. Okay, then I would ask you to answer the following survey. If you are working with two screens, I will adjust my pace accordingly. Okay, most of you have two screens. I will then begin with the first example. RSECTION is an independently executable program for generating any thin-walled or massive profiles. If you want to design special profiles in RFEM or RStab that are not contained in the profile library, you can create them with RSECTION. You can then import these user-defined profiles into RFEM or RStab. In RSECTION, it's possible to calculate cross-section values and stresses. The RSECTION user interface is the same like in RFEM 6 or RStab 9. The cross-section graphics and dialogues are displayed in the working window. Most tasks can be performed with a mouse. in the tables here below, the keyboard is primarily used for numeric input and output of results. There are 3 navigators in the left pane of the working window. It's the navigator data, navigator display, and navigator results. The data navigator manages the input data. A double click on an entry opens the dialog. Here, if I double click here on the points, and then the dialog will open, and then I can modify this point. It's also possible to open the dialogs for creating new objects. If I go to points, then it's here possible to add a new point. The display navigator, I will turn to this, controls the graphical display in the working window. If the checkbox in front of an entry is unchecked, this object is hidden in the graphic. If I uncheck here the points, you see in the graphic, the points isn't displayed anymore. The result navigator controls which results are displayed. You can change here between statical moments, unit stresses, and so on. Then I would like to go into the mouse functions. To move the section, you can hold down the mouse wheel and move the section accordingly. You can turn the mouse wheel to zoom in or to zoom out, and right-click opens the context menu. You can also select objects with the mouse. If you open a window from left to the right, everything that is completely within the selection area will be selected. If you drag a window from right to left, everything that is intersected by the selection area will be selected. You can also select individual objects. To do this, left-click on an object that you want to select. To add objects to the selection, hold down the Control key and then left-click on the next object that you want to select. To remove objects from the selection, hold down the Shift key and click on the object that you want to deselect. For the first part of the training, I am now starting a survey again. Please answer the following question about the suitability of our section. I will start it now. Multiple selection is also possible. Okay, I will close the survey. All answers are correct. Our section is suited for the creation of any thin-walled or massive cross-section and also for the calculation of cross-section properties and stresses. This brings me to the first example. To create a custom cross-section, I open the new model window via this button here. And then I have to give the model a name, and I name it here example 1. Furthermore, the analysis method must be defined. This is here in this chapter, and the following analysis methods are available. It's the finite element analysis and the thin-walled analysis. The effective cross-section can be calculated for both analysis methods after activating the extension here under the options. A standard must be selected according to whose rules the individual parts or the subpanels are to be generated, and the effective cross-section is to be calculated. The following standards are currently available. It's here the Eurocode 3 Part 1.1 for steel sections, the Eurocode 3 Part 1.3 for cold formed sections, and the Eurocode 9 for aluminum sections. I choose here the Eurocode 3 Part 1.1, and then I click on OK. The selection of the design method or the standard is irrelevant when using the R-section cross-section in RFEM or RStab. You can select the design method in RFEM or RStab regardless of what is said in R-section. Furthermore, the subpanels are generated in the design modules based on the standard selected in the design add-on. In the steel design add-on, the manufacturing type determines which part of the standard is used for the design. For cold formed cross sections, the standard Eurocode 3 Part 1.3 is used, and for hot rolled or welded sections, the standard Eurocode 3 Part 1.1 is used. Now the file is created. I first define the material, and for this, I open the Edit Material window. I can create or copy another material on the list via this button. This creates a new material, and this copies the selected material. I can enter a material name here directly. Our section then lists all materials that match that name. If I enter here as 235, then our section lists all materials with that name that are within this database. It's also possible to select a material via the material library. To do this, I open here this material library via this button. And in the material library, filters are available to me to quickly find the material. I can here filter by material type. I choose here a steel, for example. Then I see all steel type materials. But there's also a search available in which I can search for a material. I select steel S355, and I selected here from this standard, and then I click on OK. If the material is not in the material library, I can create this material by activating the user-defined material option. I can adjust the material values in this type of material values if I want to. I don't want to do this today, so I uncheck this option again. Then I click on OK. I then create the elements. The definition of elements is required if the analysis method, analysis of thin-walled structures, is selected, or if the effective cross-section is to be calculated. An element must always lie in an area. This area is called part in our section. Elements can be created graphically or via a dialog. The graphical input is called up via the symbol here in the toolbar, and the input via dialog is called up via the navigator data. If I go here, I can create a new element via the dialog. When creating an element with a graphical input, the part is also created. When created an element via the dialog box, the parts and the points of the element must be created beforehand. This is why it's not possible here to call up this dialog because I haven't created the points before. I enter here the element graphically, so I use this function single, and I enter the bottom flange here first. I choose the input mode, length, and direction, and I choose an angle on the work plane of 0 degree, and I define for the flange a length of 150 millimeter and a thickness of 10.7 millimeter. And then I left click here on the working window. Then I create the web. Elements must be connected for the calculation of the effective cross-section. The connection is to be made via the start and the end points of the elements. If two elements share the same points, they are connected. For the web, I use also the input mode, length, and direction. And here I define an angle in the work plane about 90 degrees. And I change here the direction, and then I define here the length of 289.3 millimeter and a thickness of 7.1 millimeter. And then I create this web. Then I create the left flange, and for this I use also the input mode, length, and direction. Here I change the angle on the work plane. It's here 0 degree. I change the length to 75 millimeter and the thickness to 10.7 millimeter. Now I have to create the flange on the right side. For this, I transverse the direction, and then I create this element. I now click on the right mouse button. This closes my window. The profile should be a rolled T profile to which a lower flange is welded. The round radius is 15 millimeter. I can define lines to create them or use the create round corner function. I find this function here below, and in this dialog I have to define the round radius. This should be 15 millimeters, and then I have to click on the corresponding lines. And then I click on the right mouse button to close this window. The lower flange is welded with a 6 millimeter double fillet weld. I create the welds using the create angled corner function. I find this here. And I have here two corner types, both edges, where I can define the length of the edges, or I have here the corner type edge and angle, where I can define just one length and an angle. You can also calculate in the dialog. So I define 6 multiplied by a square root from 2, and I define here an angle about 45 degree, and then I click on the corresponding lines. The subpanels that you can see here are generated based on the standard selected in the base data. These cannot be changed if no elements are defined. Cross-section classification in our section and the design and in the design modules of RFEM and RStab is not possible, and neither a calculation of the effective cross-section is possible. On the design add-ons, this cross-section is then designed according to cross-section class 3. I would also like to use this example to show you how to calculate stresses and the effective cross-section. In order to calculate stresses or the effective cross-section, a load case must first be created. Load combination can also be formed. I create a load case first, and for this I go into the navigator data and right click and choose here a new load case, and I name it N, and I want to create a second load case. For this I use this button, create new load case, and I name this load case M. And I want to define also a load combination. For this, I create a new load combination via this button. And then I assign the corresponding load cases to my load combination. It's also possible to change here the factors if you want to. Then I click on OK. Then I have to define the internal forces. The internal forces can be defined manually or imported from RStab or RFEM. If you want to use the import function, then you can do this via this table, internal forces, and then you can click on this button here, import internal forces from RFEM or RStab. I want to define the internal forces manually. For this, I go to the navigator data, and here I open the tree internal forces, and then I double click here on internal forces, and I want to define a compressive force, and the compressive forces are negative, tensile forces are positive. Therefore, for a compressive force, I define here minus 10 kilonewton. Then I click on apply and next, and I change here the load case to load case 2. And here I want to define an axial force about 0 and a bending moment my about 100 kilonewton meter. And I click here on OK. The blue dots that you can see here on the graphic are the stress points. Stresses are calculated and displayed at the stress points. The stress points are generated automatically. Stress points can also be defined manually. I want to do that here. So I go here to the navigator data again. I find here the three stress points, and then I right click on it, and then I can define here a new stress points. It's possible to define here the coordinates manually, or it's also possible to select a point in the graphic and import its coordinates. I define here for the y direction 75 millimeters, and for the z direction minus 100 millimeter, and then I click on OK. This stress point is now created. If I want to find it, I can right click on the stress point in the navigator data, and I can use this function find, and you see now the stress point is located here. Which stresses are to be calculated and output in tabular and graphical form can be set in the stress configuration, and you find the stress configuration also in the navigator data. Here under stresses, stress configuration, if you double click on it, then the corresponding window will open. And here via these checkboxes, you can check or uncheck the stresses that you want to calculate. Here, these stresses are calculated, the total normal stress, and here the total shear stress, and also the equivalent stress. I don't want to calculate more stresses, so I click on OK. I'll start the calculation now. For this, I choose here in menu calculate all. In the results navigator, you can switch between the gross cross-section, this is here the thin-walled analysis, and the effective cross-section. This is here the effective thin-walled analysis. The same is possible in the result tables. Here in the result tables, you have also the possibility to switch between thin-walled analysis and effective thin-walled analysis. Furthermore, you can switch between the results of the individual load cases, and you can also here display the stresses, and now the stresses sigma x total are shown for a load case n, for load case number 1. If you want to see the stresses here for load case 2, you have to choose that load case here. I first look at the results of the gross cross-section of load case n. The display type can be set also on the results navigator. Here you can change the type of display. I change here, I choose here off. I can see the cross-section values here for the gross cross-section. If I choose here thin-walled analysis, then you can see here the section properties. The section area is calculated. Also, the area moment of inertia about y and z axis, and so on. Also, you can see here in the tables the statical moments, and it's also possible to see here the calculated stresses numerically. It's also possible to show these results graphically. You can see here the statical moments, and you can see here also the stresses on the gross cross section. If I now want to display the stresses at a specific stress point, I have to switch here to the tab All Stresses by a Stress Point. And if I choose here this stress point that I have created manually, then the results are displayed of the stress point here on the table. In the case of the results of the effective cross-section, in addition to the results of the gross cross-section, there are also outputs for the classification of the cross-section and the effective width of the cross-section. I choose here the effective thin-walled analysis. I have here the section properties of the effective cross-section. I have here the section classification, and I see here that the section falls into class 4 for this load case axial force. Local buckling occurs in class 4 cross sections. According to the standard, the reduction in strength due to local buckling can be taken into account through effective widths. And you can see this here in the graphic. If I change here to effective thin-walled cross-section, then here the web falls into class 4, and therefore the effective widths are calculated. Here an ineffective width is calculated about 19.7 millimeters, and you can see here this reduction graphically. It's also possible here to look at the results of my load case 2. Then you can see here that the results for my load case 2, this cross-section falls in this load case into class 1, so no reduction is made. I'm now starting a survey again regarding the requirements for cross-section classification. I start this. Multiple selection is also possible. Okay, I close the survey and then I share the results. All answers are correct. For a classification, internal forces must be defined, elements must be defined, and it's necessary to activate the effective section add-on. I would now like to use another example to show you how you can access cross-sections from the library and modify them. For this, I create a new file. I click here on this button, New File, and I name it Example 2. I choose here the analysis method, thin-walled analysis, and I want to calculate also the effective cross-section. So I activate this checkbox again, and I choose here the Unicode 3 part 1.1. Then I click on OK. Then I define the material. For this, I double-click on the material and I open the material database. And here I choose this S235. And here I click on OK. And now this material is defined. Then I insert a cross-section from the cross-section library. To do this, I open here the new section and window in the data navigator. The window is structured like the material window. A cross-section can be created or copied via the list here. You can create a new section or you can copy selected sections. I can also enter the name directly here, maybe HAB 100, and then you can see here all cross-sections with that name in the cross-section library. And I can also open the cross-section library via this button here. A large number of cross-sections have already been entered into the cross-section library. I choose here standardized L cross-section. And in the cross-section library, like in the material library, I have filters here on the left or a search to quickly find the cross-section. I choose here an angle L 200 x 150 x 12, and I choose here this standard from Dean, and then I click here on OK. The angle should be mirrored around the y-axis. That's why I activate this checkbox, and the angle should be also rotated about the x-axis about 90 degree. So I define here 90 degree. Furthermore, I select the offset point in the graphic, and here I select this point, and at this point the cross section is placed at the insertion point that you can enter here. You can enter it manually, or it's also possible to pick the location in the working window. And I pick here this location, and then I click on OK. When inserting this thin-walled cross-section, two elements are created, and also the corresponding part. The cross-section can be subsequently edited. If I double-click here, this opens the Edit Section dialog where I can change or modify here the offset point locations and so on. And it's also possible to move this cross-section or to rotate this cross-section via this function here. However, in order to modify individual objects such as points or lines, the cross-section must be splitted. The cross-section is to be supplemented by further cross-section parts. I therefore split the cross-section into its individual parts, and I can do this by right-clicking on the section, and then I choose here this function explode. The fillet isn't needed, so I will delete that. I delete this point, and now the part is deleted too. Here you can see the elements are colored in red, and this means there's an error for the element. for this element. The elements must lie in part. The part is deleted, so here's an error, but I will create this part later. I will now add more elements, and I will do this via the graphical input. So I select here a single element, and I use also the import mode, length, and direction. Angle in the work plane is 0 degree, and I define here a length of 200 millimeter and a thickness of 12 millimeter. Now the direction must be changed, so I click here on reverse orientation, and then I click here on this point. Another element for the web should be created. To do this, I use also the input mode, length, and direction. Here I define an angle of 90 degree, and I have to reverse the orientation, and the length should be 400 millimeter and the thickness 10 millimeter. And then I click here on this point. I delete unnecessary lines. For this, I click on with my left mouse button on this line, and then I click on delete. And I will do this with this line also. I select it, then I click on delete. Welding seams should be also taken into account in the cross-section properties. I create the weld using the angled corner function. So I open this dialog again. I choose the corner type, edge and angle, and a 6 millimeter double fillet weld is to be defined, so that I define here 6 multiplied by square root of 2, and I define here an angle about 45 degree, and then I click on the corresponding lines. Furthermore, I still have to create the part, and I will do this using a function that I can find here. Select boundary, and for the new part, I have to define a material. This should be the created material as 235. Then I click on OK, and then I click on a line, and now the part is created. The cross section is now complete. I would now like to calculate the effective cross section and the stresses, so that I create load cases and internal forces. I create the load cases first. For this, I go to the navigator data and choose here new load case. I name this load case M, and I create another load case via this button, create new load case, and I name this a load case M. I also create a load combination. For this, I go to the tab load combinations, and I click on this button here, create new load combination, and then I add all load cases to my load combination. And then I click on OK. Then I have to define the internal forces. To do this, I go to the navigator data, open internal forces, and then I define here an axial force about minus 50 kilonewton. I click on apply and next. I change the load case to load case 2. I define here an axial force about 0 kilonewton and a bending moment about 20 kilonewton meter. And then I click on OK. Then I start the calculation. I choose here calculate all, and I look at my effective cross-section. This cross-section falls in load case 1, also in class 4. I can see here the reduction, and I can see the reduction also in the tables. I can see here the section classification, class 4, and the effective width here for this sub-panel. I also want to create a printout report, and I will do this via the navigator data, and you find here this printout reports below, and then I click here on a new printout report, and then I have to check the report items that I want to have into my or that I want to add into my printout report. I don't want to see the stresses by material or by member or location and stress points. And then I click on Save and Show. Now the printout report will be created. I can see here the numerical results. It's also possible to add graphics to the printout report. To do this, I hide this printout report, and I use here this function, print graphics to the printout report. And in this window, it's possible to define the size of the graphic. Here I choose a window filling. I can see now the preview, and if it's okay, then I can click on button Save and Show. And now this graphic is added to the printout report. I'm starting a poll again. Please answer if an analysis of thin-walled structures is suitable for the calculation of rolled parametric steel sections. I will start it now. I will now close the survey and share the results. The correct answer is here that the analysis of thin-walled structures is suitable for the calculation of rolled parametric steel sections, and you have answered this correctly. In the next example, I would like to show you that you can also create cross-sections by importing a DXF file. A DXF file can be imported via menu File, Import DXF. Then I have to choose the corresponding DXF file. And then I click here on Open. I don't want to import the DXF file into the active model. I want to create a new one. So I click here on No. And then a new window opens. In the section Create a Section Model, you have 3 options for creating the cross-section. The automatic creation of elements is useful if the outlines of the cross-sections are available in the DXF file. Our section attempts to create center lines for parallel lines and then set the elements between the intersections. Only elements that do not exceed the maximum thickness that you can define here are created. The import function use DXF template lines as center lines is useful if the cross-section geometry is available as a center line model. The lines of the DXF template are considered as the center lines of the elements. The thickness defined in the field T is assigned equally to all elements. The function create DXF template is useful for massive cross-sections where no elements needs to be created. In addition, this function can also be used for complex cross-sections where I only want to create elements for the decisive cross-section parts. With this import functions, the lines in the DXF file are imported as lines. You can then use these lines as an aid for modeling. I choose this option now, and then I click on OK, and now the lines are created. A finite element analysis is to be carried out. And to do this, I go here to the base data, and I choose here the analysis method, finite element analysis. The finite element analysis should be performed on massive cross-sections, such as timber cross-sections or concrete cross-sections, in contrast to thin-walled cross-sections, where the stresses can be regarded as constant across the cross-section thickness. The stress distribution in solid cross-sections is variable. This can only be determined with a finite element analysis. So I choose this analysis method now, and I click on OK. Then I have to define the material. I modify here the created material. This should be an aluminum material. I open for this the material library, and I change here the filter to aluminum, and then I use here the search function, and I want to define a material ENAW 6060. And I choose now this material here on the bottom, and then I click on OK. In a finite element analysis, only a surface needs to be defined. This means only the part needs to be defined, but no elements. I would only have to define elements if I also want to calculate the effective cross-section or carry out a classification. So I only have to create the part here, and I create this part via the function select boundary. I click here on OK, and then I click on a boundary line. Now the part is created. I still need to create the openings. I create the openings using a function that I find here, select boundary, and then I have to click on the boundary. I can create the other openings by rotating them. I want to show you this also. For this, I first have to select the opening that I want to rotate, and then I select here the function rotate selected objects. I want to create a copy, and I want to create 3 copies. That's why I define here a number of steps 3, and the rotation angle should be 90 degrees. Then I have to define the point of rotation. I can also pick this in the window. And if I click now on OK, the openings will be created. I want to calculate the stresses here as well. So I create load cases. For this, I go to the navigated data again and right click and choose here new load case. And I define here a load case M, and I also define a load case MT. Then I click here on OK. Then I define the internal forces, and I will do this via the navigator data again. I open the internal forces dialog, and I define here an axial force about minus 10 kilonewton in load case 1. Click on apply and next. Then I go to load case 2, and here I define a torsional moment about 0.3 kilonewton meter. And click here on OK. Then I start the calculation via menu calculate all. And now the finite element analysis is carried out. I have here also the section properties, the stresses in tabular form, and I can also see here the stresses graphically. If I choose here, for example, sigma x or tau total, here I have to change to load case number 2, and you see it now, the results graphically. I want to create for this also a printout report. That's why I go to navigator data again. Then I right click on printout report and choose new printout report. Here I choose the report items. I don't want to see the stresses by material, member, location, stress points, and so on. Then I click on Save and Show. Then the printout report is generated. I want to also add a graphic to this printout report. So I go here to this function, print graphics to printout report. This should be window filling. Then I click on Save and Show. And now this graphic is also added to the printout report. I'm starting a poll again. Please answer whether the finite element method is suitable for the calculation of massive cross-sections, such as concrete or timber cross-sections. Nearly all of you have answered this question. so I share the results. Correct answer is here that the finite element method is suitable for the calculation of massive cross-section. Most of you have give the correct answer. As a last example, I show the modeling of a composite cross-section. In our section, it's also possible to model cross-sections that consist of different materials. Ideal cross-section values are determined for such a cross-section. 1000 millimeter wide and 200 millimeter high concrete cross-section lying on an HEB steel cross-section is modeled in this example. For this, I create a new file and I name it example 4. I choose here the analysis method finite element analysis, and then I click on OK. I define two materials. For this, I open the material window, and for the first material, I define a steel material. This should be an S235. I open for this the material library, and I choose here the S235 material, and I add a new material, a second material to the list. I will do this via this button, create new material. Then I open the material library again. I choose here the material type concrete, and I choose here C3540. Oh no, I want to choose here a C4050 material. Then I click on OK, and also OK. The first material is always the reference material. In RStab or RFEM, however, I have the option of defining other materials. First, I model the concrete cross-section with a dimension 2000 to 200 millimeter, and I will do this via section. So I go to Navigator Data, New Section. Then I open the section library, and I choose here a massive rectangle cross-section. Then I define for B 1000 millimeter, and for H 200 millimeter, and I define a material, the concrete material for this. Then I click on OK. Now this cross section is inserted into the file, and I create a second cross section. For this, I go to Navigator Data again, New Section. This should be the steel cross section. For this, I open here again the section library. I choose here I-beams, H-beams, and I define here an HEB of 400. I choose this one. I choose the material S235. I click on OK, and I choose the center of the top flange as the offset point. So I click here on this point in the graphics, and I choose here the section location, here the bottom of the concrete rectangle. Then I click on OK, and I want to calculate also the stresses, and for this I create a new load case. So here I go to Navigator Data, new load case, and I define the load case name M. I click on OK, and in load case M, I define a bending moment about y-axis about 100 kilonewton meter. I now start the calculation. I can see here now the stresses, and I would also like to show you how to import the cross-section into RFEM. To do this, I first save the cross-section, and I now open RFEM 6, and I create here a new file. I name it example 1, and then I click on OK. Then the new file will be created. Then I import the section cross-section into this file first. For this, I go to Navigator Data, and then I right-click on Sections, New Section, and then I open the section library, and here I have the possibility to import a section from our section. I click on this button, and this opens the Dlubal Center. And in the Dlubal Center, I choose here this example 4. I click on OK. And now this cross-section is available in RFEM 6. I have here also the tab hybrid, and here you can see the material assignment, and if you want to, you can also change the materials here for the parts 1 and 2, and it's also possible here to change the reference material. It's also possible to create a member with this cross-section. To do this, I click here on New Single Member. Then in Tab Section, I choose this cross-section. This is my example 4. And then I create this member. With this example, I have come to the end of the training. It was taught how you can create general cross-sections with graphic functions, how you can add cross-section parts to database profiles and create profiles based on a DXF import, and also how to create hybrid cross-sections. Finally, I would like to show you where you can find more information on our website. You will find in tab Support and Learning frequently asked questions. You can find here also a knowledge base articles on news and events. You can find our webinars. I hope that the training for using our section has helped you, and I thank you for your attention.